So hello everyone, welcome to this webinar related to the supply modeling in THERMOS. This will be one of 3 webinars that we'll be developing based on the needs of participants from the support facility, and also basically to showcase the results of both support facilities. So today we'll be covering, as I already said, the thermal supply models. Here we have with us Martin Hawley, which is the head of the consultancy department for CSE. And we also have with us Tom Hinton, who is the head of software development. Basically, the agenda that we have for today, you can go to the next slide, please, Martin. Will be basically an overview on the functionalities of the tools. Basically, first an introduction to the thermal supply model, and then the run through of parameters and outputs, which will be done by Martin. Basically, yeah, as I already mentioned, cover it from more technical perspective, and then we'll have the demonstration of the model done by Tom. So yeah, that's all on my side. Just leave the floor to Martin. You can start whenever you want. Thank you.
Okay, thanks, Juan. So yeah, oh, it's somebody else. Oh, it's Alistair joining. I'll just let him in. Okay, here we go. Right, so I just advance the slides onto the first one. So what I thought I'd do first of all is just give a quick recap on THERMOS itself, THERMOS features. So I mean, this is specific. This session today is specifically on the THERMOS supply model, but I think it helps to just recap on THERMOS itself. And what you can see there are the sort of the main processes that people would typically use in going through THERMOS. First of all, you've got the data preparation in order to do a number of things, but including, first of all, the estimation of demand for heating and cooling, which uses, but there's a range of techniques for doing that, but we can use sort of LiDAR data so it's a case of preparing that and sourcing it, or other locally sourced data as well, and any supplementary mapping data that you can get. Then once you've prepared all that data and got it into THERMOS, yeah, the model can then estimate the actual demands for the buildings that you're looking at of interest. And yeah, it does that in a number of ways, as like a hierarchy, really, in terms of the accuracy depending on the data that's available. So it's flexible in that respect. And it will then kind of produce a heat map for the outputs of that process, those calculations. So that's the sort of first stage of THERMOS, is trying to categorize the demand for the area and the buildings of interest. And then the next procedure is really to start creating and developing scenarios for heat networks or cooling networks of, you know, what you think might be might have the most potential. So there's the feature of the facility to select buildings of interest, and either make them optional or make it so that the model, you know, definitely includes them. So you can set objectives along those lines, and you can also, in a kind of fairly basic way, define a heat supply. So we'll talk about how that links to the supply model in a bit. You set objectives around economic and technical parameters as well, and you can then optimize those networks repeatedly. So that's the big benefit of THERMOS, is that you're very easily able to iterate the analysis and you know, compare different scenarios and tweak things and run things again. So that's the network itself, and the idea is that you will then have some optimized solutions for a heating or cooling network. The other feature, which we'll talk about in more detail now, is the optimization of the energy supply. And then, of course, with THERMOS, you've got the results that it produces, and there's several options of how you analyze those, and how you the format that they take depends on what they're being used for. But yeah, there's a lot of flexibility there. So THERMOS, as you probably know, it was developed from a European funded project, which completed a couple of years ago, and there's a free version, online version out there for people to try. It is being quite widely used now, as far as we're aware. We know that several thousand people have registered users of THERMOS, and it sort of spreads across Europe and global in terms of users. So we've had quite a lot of feedback on its application so far. But I think interestingly, the energy supply side, the energy optimization of the supply is one feature that hasn't been that well used within THERMOS compared to the network optimization side of things. So we're quite interested to explore this a little bit more, and try and get some case studies going on this. So let's start by just describing what the actual thermal supply model is. So it's, as I said, it's like a feature in THERMOS that sits alongside the network optimization side of things. And it aims to determine a set of choices on how to develop an energy center to meet a certain demand, a certain heat demand. And it does that by considering a couple of questions around the technologies, supply technologies to draw on, to purchase, if you like, and how much heat to source from each of those technologies, whether there's one or multiple sources, and over what time period. And there's also a storage element here, so the model has to make decisions on what heat storage to purchase, so what technologies are going to use there and how much heat to store. The big difference with the supply model compared to the optimization model for the network is that it needs to consider the supply of heat over time, whereas the network model considers basically distance, looking at spatial issues. So what it does is that it uses the outputs from the network optimization, which are fairly basic on the supply side, and then it does some fancy work to transform that into heat load profiles for the buildings of consideration. And yeah, as I said, there's supply technologies involved there, also substations where they're needed and relevant, and energy storage as well. So this just kind of gives an overview of how it works, how it kind of integrates with the network optimization side. So on the left there, I've just described that with the network optimization, modeling heat demands, optimizing the network route according to whatever objective you've chosen, and you've also got energy center location there and the heat supply requirements. So the actual outputs from the network model are, as I said, fairly basic in terms of heat supply. You've got or demand. You've got a list of buildings which are connected to the heat networks for that optimized network, and for each of those you've got peak heat demand, like in kilowatts, and you've also got annual demand in kilowatt hours for each of those buildings. But you've also got then to sum all of those taking into account load diversity across the network to give sort of one set of figures really for the supply point in terms of kilowatt peak and annual kilowatt hours demand. So those are the figures, the key figures that are used in the supply model. So it's important to optimize the network before you start looking at a supply model. And those figures in themselves are not accurate enough. They're too limited to actually inform the supply model to the extent we need to. So as I said, there's several ways that it applies to convert those figures into load profiles for the buildings that we're talking about over many time intervals. And yeah, it needs to do that before it can then optimize the supply scenarios that have been set up. So just talking about that in a little bit more detail. And here we're showing some of the snapshots from the model itself, which Tom will be going through in a bit. So one of the first things that the user needs to do is start defining certain parameters. And here we're talking about load profiles. And of course, the whole reason for this really is the fact that energy prices can vary across time periods, across days, across weeks, years, across the year. So you have the model offers different day types to divide into intervals, and so the default there is you got 5 day types: at normal weekday, normal weekend, winter weekday, etc., where you set up a profile for those. And the idea is that the whole year will be made up of a mix of these different day types. And then you start to look at the heat profiles for those, and you can enter those numbers sort of on a relative basis for different types of buildings, different groups of buildings. And you then look at variables for fuel prices and emissions as well. And for example, grid offer, that's sort of looks at the price that you might be selling electricity for in the case of CHP generation. So yeah, the end result really of this process is a heat demand that the supply needs to provide for each of these intervals that you're trying to define in each representative day that's being modeled. So so this is where we're looking at typically half hourly or maybe hourly intervals across the day, and trying to define what demands look like and other parameters within those profiles. In terms of technologies, this is again where the user can start to define these and specify a whole range of parameters there. And the model will then select from these and decide which ones are most advantageous to purchase heat from in the whole optimization process. There's also substations involved, as I mentioned. As you probably know, substations have kind of a limitation in terms of what we call headroom, which is basically their capacity to kind of supply electricity from the grid to the consumer, and also accept electricity going in the other way, the reverse direction. So that needs to be considered as well. And there you've also defining storage technologies for the model to again decide whether it's advantageous to include those, and to what extent, and which technologies as well. And the other thing, obviously, similar to the network optimization, you need to set some higher level kind of objectives around accounting periods and discounting, so so it can do some sort of basic economic financial calculations and come up with some outputs. There's also a curtailment cost, which kind of allows, in a nutshell, it allows the model to undersupply heat in a given interval to avoid the problem from becoming infeasible. And Tom will probably explain a little bit more about that. And also things like heat dumping. So this is where if you got CHP, for example, you can decide whether the system will be electricity led or heat led in the way it's operated. And then, of course, emissions, you can set costs of emissions there on which the model will then kind of base the outputs. And the other thing, just to mention at the bottom, this is a bit about computing resources. This is a bit more relevant to network optimization because that's a lot more complex and can take a lot longer. But generally speaking, the supply model is fairly fast in the way it runs. It's not quite so complicated, and you should get fairly instantaneous results in most cases coming from that. So just to cover very briefly a little bit about outputs. So yeah, once the model is run and you've got some results, then the results are kind of split by those areas there. You've got a total cost summary. It looks at plant and storage features in the solution, heat production, fuel consumption, grid export, and emissions, of course. And you can upload and download information data as a spreadsheet, similar to the way that you can with the network optimization model, which can be useful as well. It just saves a lot of data entry, especially, you can download a spreadsheet and then make some changes and then upload it to speed things up in your setting of scenarios. This is just looking a snapshot of what the total cost summary looks like, and the kind of parameters that it will churn out, and categorized by the type of technologies. And you notice the figure there at the bottom, average unit cost of production. That's quite a useful figure to come out of it. The cost of heat per unit, that's a good comparator, it's a good KPI then to compare with maybe other scenarios that you're running and how it fits with the network that you've optimized as well. And then, yeah, there's in THERMOS outputs, as Tom will be looking at, there's a whole raft of graphics that show profiles of heat production and the various contributions from the different systems, the different technologies that the solution is made up of. And yeah, it just splits down all those results in energy terms, but also in financial terms. So that's just a very quick overview of what the supply model looks like and the kind of things it covers. Tom will be now going through basically the same thing, but actually showing you how it works on THERMOS. So it will, I think that's going to be really useful for you to see that actually applied in practice. He'll be going over some of the same stuff, repeating some of the stuff that I've said, but I think that's fine because he'll probably explain some things better than I have, and I think it will. Yeah, you'll relate to it better once you see it being demonstrated within the tool itself. So if I stop sharing now, I'll hand over to Tom, who will just talk you through what it looks like on the actual model.
Hi. Can you remind me how long you want me to talk for, Martin? I forget. Or just until I got to the end.
I think yeah, what's the time? So I think we're looking at like 15-20 minutes.
Sure.
But
okay.
I think it's fairly flexible.
Mm-hmm.
Yeah, as much as you need, Tom. It's fine.
Okay.
Yeah.
So let me show you a. This is a THERMOS model of a system in Bristol, in Redcliffe. So this is the network model, which you're probably all familiar with. And I'm just going to close my window. So, oh no, it is closed. It's just noisy outside. Sorry about that. But yeah, so this is a network solution in which there's a single supply modeled here. And then if I switch it to show what it's actually chosen, this red bit is the network that we're modeling, with some loads at the ends. And I guess, like Martin described, in this part of the modeling, what is understood about the supply is fairly limited. So the parameters that go in are just these facts. So it's a small handful of numbers. How big a thing could you build, and a few kind of indicative sort of unit costs. But practically these costs will depend on when the load happens and what mix of technologies you end up building. So the purpose of the supply model is to kind of, I suppose, get you a more correct or a more detailed understanding of these figures. So as Martin's slides kind of illustrated, there's sort of a bridge between the two models. They're really two separate models, the supply part and the network part. And the outputs from the network model form inputs to the supply model. So kind of in summary of that, if I look at the supply that the model has built here, this fact is the sort of critical bit of information. Hang on, let me just look at these. Yeah, this is my broadhouse here. Okay, so yeah, it has some necessary capacity here, and it will also have a kind of an annual output figure. So we can see that stuff in the in the sort of operating summary for the network. It will tell you, you know, it's built this supply, it's 5 and a bit megawatts, it's so many gigawatt hours a year of output. But really, this is all that the network model has understood about the supply, is just that these numbers here. So it doesn't tell you anything about time of use. So to sort of get it to do the supply modeling, I suppose in here, once you've solved a network model, there's a few extra things that you might want to tell it, which will be on the demands in the solution. There's some information about load profile. So this is a representation of the time of use for heat in the building, and those are kind of inputs to the supply problem. So the profiles are sort of defined here in this slightly ugly bit of user interface. You can get these out in a spreadsheet and edit them yourself and put them back in. So the load profile sort of theoretically is like an annual description of the shape of the demand. It doesn't represent every single time unit in the year, because that ends up being a lot of data to produce, and then a lot of decisions for the model to make, because ultimately it's making operational decisions about what output you should get from different parts of your energy center in all of the time periods in the year. So the year is instead represented as these characteristic days, which have a certain frequency in the year. So this in this default set of parameters that the model has in it, there are 197 normal weekdays in a year. There are 78 normal weekend days in a year, and then there's 62 wintry weekdays in a year, 27 wintry weekend days in a year, and then there's one peak day, which is the sort of maximum day across the year. And the profile is defined by these kinds of rows of numbers, which are sort of dimensionless quantities. I mean, you could think of them in kilowatts, but all that really matters is their relative scale. So for this one, which is a peak day, the peak time is here, and it says 2.41. That's every other piece of time in the year is going to be sort of relative to this value. So there's kind of an explanation of this actually in the help, which I'd probably recommend reading if you do end up using this. So looking in the help, there's this section on the relationship to the network model, and this describes how these load profiles are reshaped so that they connect up to the values in the network model. So anyway, there are these load profiles. They give the shape of demand, and you can add more if you want to by clicking this plus button here to describe different types of buildings. So in the defaults, we've got a sort of residential one, a commercial one, and then there's one called flat, which is for, it's one all the time. So it's saying consumption is the same throughout the year. That's flat as in continuous rather than as in a block of flats. So if I take a few of these loads in my solution, let's say that one, I could say this one, let's say that one has flat demand because it's some sort of industrial process that runs all the time. And then I don't know, let's say that these ones are commercial, and then the remaining ones are probably residential. Maybe yeah, that looks okay. So now if that's all the setup necessary in the network side of it, is to say, well, here are the buildings, here are their demands, here's the supply, here's the total load on the supply that comes out of the network model, and then here are the shapes of the profiles. And then if I press optimize and then press supply, it will go away and come back with a solution. As Martin said, the supply model is pretty quick. That was it. And what it will have done then, if we have a look at the summary, is it will have made some decisions essentially about what to build. So the things it's built, first of all, this is the sort of roster of things to construct, and I'll go through the parameters of these a bit later on. But it's said I want to build a gas boiler, probably for peak, a heat pump, probably for covering most of the sort of base, and then a bit of thermal storage, probably to balance electricity price when running the heat pump. That would be my guess as to what it's decided to do or why it's decided to do it. And yeah, these figures you can get broken down by different types of time if you want to. So these are the sort of operating decisions the model ends up making. So each of these graphs is telling us, so this is heat production, so this is what's output from the system, and each of these is for one of the characteristic days. So I guess here you can see a number of things. You can see the in these ones, you can see the shape of the overall load profile. So this is some combination, but you can see the effect of the choices I made in the network editor. There's a sort of baseline here, which is probably caused by the ones I set to be flat, because they're on all the time. So that will be this sort of 1 megawatt demand that exists pretty much all the time. And then there's a bit of wiggly stuff, and this is some combination of the commercial and the residential profiles that I chose, scaled to fit the demands of the buildings in question. So on these typical weekday, typical weekend, pretty much all the heat is coming from heat pump, and the peak is kind of what, 2 and a bit megawatts. But then you can see that on these winter days where the peak is a bit higher, so winter weekday, the peak is about 5 megawatts. The system is instead running the heat pump continuously at this sort of its maximum output, the size it bought, and then it's cheaper to cover the peak by a bit of storage. So the actual shape of the profile of the demand profile probably goes down a bit here, or down a bit here. And what's going on is the heat pump will be outputting more than it needs, or more than the network needs here, putting it into the storage. And then later on here, you can see it's coming out of the storage. And I suppose the decision to do this is all based on, or the driver is cost. So there's kind of capital costs of the stuff. So the storage costs something to build, let's say, but then there's operating costs of the electricity that has to go in. So if in the input data, the electricity price is particularly high, let's say in the middle of the day, which is probably true, or higher this time and this time, then that's probably why it's made the decision to build heat pump up to a certain size, but then past a certain point, it's worth paying for the storage. Oh, interesting. It's built this very tiny amount of gas boiler, and I can't even see on the graph when it's using it. So it's probably just that there's a microscopic period where it's worth doing that. And then these tables are just sort of tabular versions of the same thing. So that's sort of the output of the system. And then the consumption, fuel consumption, yeah, it is basically all electricity. And you can see the consumption profile in terms of kilowatt hours and the size of the peak. So again, as you'd expect from seeing the other graphs, on the normal days, the electricity consumption pretty much follows the heat. But then on these peak or the days where it's using the storage, the electricity consumption ends up flat because we were running the heat pump all the time. And there's a bit of stuff about emissions as well, but this will all be zero because I didn't put in any emissions factors. So that's sort of what it ends up outputting. Those are the decisions it's making, and then we can come back round to the sort of drivers for those decisions, and maybe I'll change something and we can see what happens. So the choices it's making are kind of between units of heat supply and storage. And then there is also this concept of a substation, which is to do with electricity capacity limits. But I won't go into that in too much detail. It's not all that interesting. So for the technologies, there's a kind of a notion of a fuel, and there are prices for that, which I'll come on to. And then there are various costs, as Martin described. These things are all written up in the help, by the way. And similarly for storage, there's some costs. There's an efficiency, which is kind of how much you get out. If you put a megawatt hour in, you get 0.9 megawatt hours out or whatever. And yeah, you can add more kinds of technology if you want to. And then the final sort of element of the cost is the second set of profiles, which match up with the heat profiles. And these are prices for things. What do things cost? You've got grid offer, which is how much will the grid buy your electricity off you for if it builds a CHP. And then you've got price of electricity, price of natural gas. So these are all flat in this set of parameters, which has probably made the results a bit less interesting. But if I were to say, let's say the electricity is substantially more expensive on the peak day and on, I don't know, winter weekends, and then run it again, and I expect it will build more gas boiler or a CHP or something like that in the solution. Let's have a look. So it's built, yeah, a bit more gas boiler, because here we go, and now we can see a bit more stuff in the outputs. So this now is saying on the normal days when the electricity is quite cheap, we'll run a heat pump and use a bit of storage. But then on these other days where I've said, particularly on this one where I said electricity is extraordinarily expensive, it makes sense to buy a gas boiler and run it only at that time, because gas is cheaper then. And similarly, on this winter weekend day where I put the electricity price kind of in between, it's decided the trade-off is, well, we'll build gas boiler, but it's only worth buying a gas boiler up to a certain size, so we'll run it up to its limit, and then we can make up the rest with a heat pump because it's a little bit cheaper. So that's the sort of thing that the model does. And you can see here slightly better, we'll use a bit of gas and a bit of electricity, let's say. Yeah, that's about the size of it. I suppose, like Martin said, you can also get these parameters out as a spreadsheet, and you can edit them and then put them back in, which I would recommend if you want to do anything with the load profiles, because typing stuff in here is tedious. So yeah, that's about it. I'll stop there. Thanks.
Okay, thank you for that, Tom. Great presentation, really hands-on, and complementing what Martin has told us before. So great. I think it made for a great webinar. Now we plan basically the Q&A section, but I think we won't get much questions since we don't have a lot of participants. But however, you can always get us your questions directly through either the THERMOS page or the ActionHeat page, and we'll try to solve them as quick as possible. We are also really interested in knowing what you think about the tool and other possible functionalities that you could be interested in us developing or yeah, supporting you on any regard. So yeah, I open the floor for any questions that there might have been, but I've been looking closely at the chat and it seems that we've got none of them. So I think that we could close the webinar right now. Thank all our speakers, Tom and Martin, for your presentations, and yeah, basically see you in the next one. Bye. Thank you.
Thank you.